Next we are going to discuss magnetic torque. So forget about magnetic torque. What is the general meaning of torque? Okay, so let us say you have a door like this, right? Now this is where it is attached and here is the door knob, let us say. Okay, now if you try to push the door open by applying pressure on this side, right, at the very end of the door, okay, it is easier for you. Now imagine you want to open the door by applying pressure at this point. Okay, is it not going to take more stress, right? It's going to take you more work. Now imagine you apply the force here. Will there be any torque? There will not be any torque. Okay, so basically the torque is depending on the distance of the point of application of force and the axis of rotation. This is the axis of rotation. Okay, so if you apply farthest away from the axis, if you apply force farthest away from the axis, then there is going to be more torque. Okay, as you come nearer towards the axis of rotation, the torque is going to reduce. Okay, so torque is given as R bar cross F bar. Okay, here R is the displacement vector starting from axis of rotation to the point of application of force, and F bar is nothing but the force vector. Okay, so this is the expression for torque. It is the cross product of R bar and F bar. Okay, let us now see the torque that is experienced by a current carrying loop when it is placed in a magnetic field. Okay, so let us say these are the magnetic field lines. B bar is the magnetic flux density. Okay, so here you have a rectangular current carrying loop. Okay, so the current is I. Say this length is L and the width here is W. Okay, now we will see what is the force experienced by it and if there is any torque that is acting on this current carrying loop. Okay, so if you take this as A, B, C and D. Now what is the expression for magnetic force on a current carrying wire? It is I L bar cross B bar, right? Now if you see this AB and CD, these are parallel to the magnetic field lines. The length vector, the displacement vector is parallel to the magnetic field lines. Okay, so then what will be the force in that case? It is going to be 0. Okay, so force on AB and CD is 0 since they are parallel to the magnetic field lines. Next, consider the other two sides BC and DA. Okay, so this is going to be a non-zero force. So what is the force for BC? If you take BC, the length vector is like this, I L bar. Okay, and this is B bar. So if you are putting your fingers, your four fingers, the four fingers of your right hand along this I L bar and you are binding it towards B bar, then what will be the force direction? It is going to be into the plane. Okay, so force on BC is into the plane. If you consider DA, what is the vector here? I L bar is in this direction, B bar is in this direction. Okay, so here the force will be out of the plane. Force on DA is out of the plane. Okay, so you can see that the length is same, I L bar cross B bar. In the expression, I L bar is same, B bar is same. So the magnitude of force on both BC and DA is the same, only the direction is opposite. So when the direction is opposite, equal and opposite, then what will be the resultant force? The resultant force is going to be 0. Okay, therefore total force acting on the loop is 0. But you have to observe one thing here, the forces, both the forces, they are acting on two different points. What will happen when the force is acting, equal force is acting on two different points? A torque will be created. Okay. So because this BC is going to experience force into the plane, AD is going to experience force above the plane, so it is going to rotate about this axis. This will be the axis of rotation. Okay. So you can write down here, torque is created since force is acting on different points. Okay. Now what is the magnitude of this torque? So if you take the current carrying loop like this is the axis of rotation. Okay. So the point of application of force, this is BC conductor and this is DA, right? So the point of application is at what distance? It is at a distance of W by 2. Here also at W by 2. So what is the torque that is acting because of AB only? Okay. The torque, the resultant torque is acting on the loop, but because of AB, how much is the torque? Okay. So only the magnitude if you take, it is going to be BIL is the force. Okay. IL bar and B bar they are perpendicular. So BIL will be their cross product. Okay. Into the distance, into W by 2. Okay. Into the angle between the distance from the axis of rotation and the force. Okay. So you can see that they are in perpendicular direction. So here sine 90. So you don't have to consider about the angle. Now you can simply write sine 90. Okay. So similarly TDA, this is also going to be in the same direction, right? The torque is going to be in the same direction. Okay. So therefore total torque, these both are in same direction. Okay, that means both of them are making the loop rotate in the same direction. So total torque is equal to 2 times BIL into W by 2. So this is going to be BILW. Okay. So this is the total torque. Now what is L into W? L is the length, W is the width. This is nothing but the area. Okay. So this is equal to BIA. Okay, where A is equal to L into W is the area of the loop, of the rectangular current carrying loop. So in this case we have taken the loop to be, the normal of the loop is perpendicular to the magnetic field, right? But what if you take, this is the magnetic field, initially we took the loop like this. So the normal vector is going to be either into the plane or out of the plane. Okay. So it means the normal vector is perpendicular to the magnetic field. But what if this is the magnetic field B bar and the normal is making an angle, some angle with the magnetic field A bar. So this is AN bar, the normal vector to the plane. Okay. So in that case what will be the torque? It is going to be T is equal to BIA sine alpha if the normal vector to the plane, normal vector to the loop makes angle alpha with the magnetic field. This is one point. Now let us say the loop is having n number of turns, something like this. Okay, so there are n number of turns. Then what will be the torque? If the loop has n number of turns, then you can take it like on each turn this much torque is acting. So on n turns, n times this torque will be acting on it. Okay. So in this case, T is equal to, magnitude of torque is equal to BINA sine alpha. Okay. Now we will see what is the magnetic dipole moment. So the torque expression, we have got the magnitude of torque. This is equal to BIA sine alpha, right, for a single turn. Now what is the angle alpha? It is the angle between the normal vector and the magnetic field. Now say this term I into A, we take as a vector. Okay. So IA AN bar, AN cap. Okay. So this we take as the vector which is having a magnitude I into A and direction which is normal to the vector. Okay. Where AN cap is unit vector normal to the loop. Then we can write T bar, the vector form. Till now we just discussed the magnitude. So we can write as, this is one vector AN cap cross B bar, right. So then we are going to get this expression BIA sine alpha. Okay. So now this vector, this is what we call as the magnetic dipole moment. Okay. So this is represented by M bar, the magnetic dipole moment. So what is its magnitude? The magnitude of the magnetic dipole moment is equal to the product of current and area of the loop. Okay. And what about direction? Direction is same as the normal vector to the loop. Okay. Normal to the loop. Okay. So we can write M bar is equal to IA AN cap. Therefore, the torque vector is equal to M cross B bar. Now one important thing here is, this is not just applicable to only rectangular areas but also for any loop of any arbitrary shape. The only condition is that it should be planar. Okay. So this is applicable for a planar loop of arbitrary shape, of any arbitrary shape.